So welcome back. We are continuing here our first lecture, and the emphasis in this clip is going to be on vector spaces. And the reason why we're looking at vector spaces is because of this first postulate, which describes the state of the system as a vector in a generalized vector space named state space, which means that a lot of the formalism that is applied in vector spaces and in linear algebra can be transferred and generalized to quantum mechanics. And this is absolutely powerful. So we're going to start and have a look at this. Just to make it clear once more, our motivation is to understand postulate 1 of quantum mechanics, which states that you can describe an isolated system using a vector in state space. And we're going to focus a lot on the generalization of vectors and the ensuing formalism. And this is used, all this concept of vectors is used in many areas of science, like linear differential equations, Fourier analysis, etc., and obviously quantum mechanics. So if we have a look, just let's start from the most boring formulation ever. So we start considering two vectors in a 2D plane, A and B, two entry, so R2, assume they are real. We're going back to basics. And if you would tell me now what makes a vector, where would you start from? What is the vectorness of this vector? So if we would like to have a look at what makes a vector, let's draw three vectors. Let's consider here vector A on the left, vector B in the middle, and let's sum both and construct a vector C, which is on the right. So what properties does this vector have? All of the three, actually, not only one. Well, the first thing you see is that they have a length, right? A has a length, B has a length, C has a length. Also, they will form well-defined angles among themselves. If you get a pair of vectors, there's always a well-defined angle, right? So this means also they have a direction. Also, they can be added, right? We added A and B when we got C. They can be decomposed, so you can write them as sums of other vectors. For instance, if you use x's, you can really see that you can decompose them into sets of coordinates. They have a scalar product. You can define a scalar product with regard to them. So you multiply those vectors in a way that you get a scalar out of it. Also, you can multiply two of these vectors so that you can get a vector product. And if you multiply them by a real number, you also get a vector that is parallel to the original one. For instance, get lambda A, it's going to be parallel to A, lambda B, parallel to B, lambda C, etc. So these properties, they seem obvious, but they are very useful if we need to understand what is going on, especially if you're breaking new ground. So we're going to go one step further and make them more formal. So let's do that. Let's talk then about vector addition. We know that for every pair of vectors U and V, there exists a vector U plus V such that the vector addition operator satisfies the following properties. So what you're doing now is we're not just going, this holds and this like this. No, we are looking at our axioms, we are really going into detail, and we're analyzing the structure of this operation that we are performing, right? So addition is associative. So if you have vectors u, v, w, doesn't matter if first you sum up v and w, or if you sum up first u and v. It's also commutative. So u plus v is the same as v plus u. Doesn't matter what order you get. There's also a zero vector. So u plus this zero vector is going to be u for all vectors. And every vector has an additive inverse. So for every u, there is a minus u. And if you add u and minus u, you get the null vector. And this is something we are trying to generalize to our state vector, to our Hilbert space, if you wish, okay? Also, vectors, they obey what we call scalar multiplication, meaning if there is a scalar lambda and you multiply each vector in this vector space, there is going to be another vector lambda a, where lambda is a real or complex number. And this scalar multiplication has to fulfill the following properties. First, it has to be associative. So lambda 1, lambda 2, if you multiply first lambda 2, and then you come up with lambda 1, is the same as if you multiply lambda 1 and lambda 2 before, and then you multiply by a. And if you combine with scalar multiplication, you can also say they are distributive. So you have lambda multiplied by a plus b is lambda a plus lambda b. And you can also say if you have lambda 1 plus lambda 2 multiply a is lambda 1 a plus lambda 2a. So this thing seems obvious, but it's nice to have these things in mind always. And if you want examples which are not as trivial as vectors in the R2 or R3, think about polynomials, for instance, because you have polynomial P1, so P1x is x2, for instance, P2x, x3. You can construct a polynomial P3, right? And you can see that this is also a polynomial. So here, notice what we have used. We have used sum, and we have used also scalar multiplication. So these properties, they have been well defined. We are satisfying all these axioms, and you can see that polynomial functions behave like vectors. So actually they define a vector space. And you also have the zero vector, which is if you have fx equals 0, as fx plus pnx is still the same pn, where n is some generic number. So we can define a zero polynomial. You can also define minus p3, minus p2, etc., as we had before. So if you don't believe me, please feel free to test all axioms and you'll see that they hold. Do have a look, because this is actually important. This looks trivial, but it's good to know where you're standing, especially if one day you're breaking new ground. Imagine those people developing the mathematical framework of quantum mechanics. They were coming up with things. So they needed to have axioms, and they needed to see that these things were rigorously holding, like really without exception. Otherwise, the framework wouldn't make any sense. Also now, remember wave functions and state space vectors if you want. Remember the principle of superposition, right? That you can always write a wave function as a superposition of other wave functions. For instance, something we use a lot if we're dealing with eigenstates of a time-independent Hamiltonian, or eigenfunctions in this case. Also, this is something that looks pretty much like the properties we have seen in terms of sum, and also this product with a scalar, right? Behaving like a vector. Also, we talked about length here. So what do we mean? Well, a vector has a norm. So if you want a more fancy way of talking about length, you talk about norm. So a norm is a function which associates with each vector a non-negative real number. So if you look at this simple example of the vector in 2D space, that's pretty much what you're doing, right? And also the norms, they have to satisfy certain properties. For instance, they have to satisfy scaling behavior. So if you have the norm of a scalar multiplied by vector A, has to be the modulus of that scalar and the norm of A. Also, it will only vanish if B is the zero vector. Okay, unless you tweak it. Sometimes you talk to mathematical physicists and come up with new stuff, but let's not go there, okay? It's not relevant for us at the moment. And the norm of two vectors which are summed, like norm of sum of A plus B, whereby their vectors is smaller or equal than the sum of the norms, which is the triangle inequality. All this makes sense to us. Why are we spending a lot of time on that? Because you are going to need to check these properties, and you know, if you don't know and you're trying to generalize a vector space, you have to ensure that they hold. Axioms are like the law, they have to hold. So any vector space in which a norm is defined is called normed vector space. So we talk always a lot about normed vector space. And if you want to generalize this, we can talk also about inner products. We're coming back. But for instance, just get the normal Euclidean space, right? Define a real vector. This vector has a length. And when you calculate the length, that's how you calculate it. And if you look, all these three axioms are going to hold. Axiom 1, 2, and 3, right? So this is what we call Euclidean norm. Now, if you didn't have real space, if you had a complex vector, how would you define a norm? So see that we modified the definition a bit. So instead of having the square of AI, where AI is like a component I of this vector, and then taking the square root, we said modulo square. Why are we doing that? And that's where the axioms come, because you need to guarantee that the axioms are going to hold, which means that we needed to tweak this, or whoever was the mathematician who was inventing this stuff needed to tweak this to make it non-negative and to make it real, right? Very clever. If you start to look up at it in more detail. And you can also generalize this. And for instance, if we talk about functions which are continuous, right? So we can generalize it. You don't have to have a sum, you can have an integral. And if you define a norm as an integral, you can also see that if the function is complex, a complex conjugate is going to ensure that this is real. Axioms must hold, and this is non-negative. Once more. So moving on. This norm is going to depend on the range of integration, and this is really important because sometimes this integral may diverge. And when you're constructing wave functions, you have to be extra careful because not all of them are really well behaved. There are areas of physics in which people deal with this kind of stuff. So you need to bear in mind that there's no guarantee that this is going to be converging. So we talked about norm. Let's talk about inner product. So if you have two vectors A and B, you can define a function which is often written in that way, which associates with each pair of vectors a complex number. So this is the inner product between two vectors A and B. Is parentheses, and you have A, and then you have comma, and you have B. Also, there are many properties that this inner product must fulfill. For instance, it has to be linear in the second argument. If you take the inner product of a function of a vector with itself, it has to be positive definite, because effectively it's going to be the square of the norm. So it's only going to be 0 if A is the null vector. And also there's conjugate symmetry, which means that if you interchange the order of A and B in that parenthesis, you're going to get the complex conjugate. So the inner product of A with B is the complex conjugate of the inner product of B with A. And these axioms are quite important when you're trying to generalize it or go into uncharted territory. Please note that the inner product is antilinear in the first argument. We said, okay, if you put lambda in front of B, which is the second argument of the norm, you're going to get a linear function, because it's going to be A lambda B inner product is going to be lambda inner product AB. But what happens if you put in the first argument? Then it's going to be what we call antilinear, because you don't get lambda, you get lambda complex conjugate. You get the conjugate. So you can verify this, in fact, by imposing that the axioms hold. And if you apply axiom 3, you know that this inner product that I wrote in the first line has to be the complex conjugate of the inner product of B with lambda A. And I know by axiom 1 that the inner product of B lambda A has to be lambda inner product of B with A. So I can pull the lambda out, because this is linear in the second argument. So now I have lambda star and the complex conjugate of the inner product of B with A, which by axiom 3 I can write as inner product of A and B. So you see that, in fact, this antilinearity is a consequence of the fact that these axioms must hold. And a vector space with a well-defined inner product is called inner product space. We have seen this when we talked about the first postulate. We're talking about an inner product space. In quantum mechanics, for vectors in state space, we define the inner product like this. So if you take the inner product of two vectors in state space, you're going to have this bra and this cat. And for wave functions, this we also know. And you can see the complex conjugation is going to guarantee that this thing is going to fulfill all those axioms, right? So let's move on. And all these axioms, they ensure that the inner product can be used to define a norm. So given a vector A in any inner product space, the norm of A is going to be square root of the inner product of A with itself. Fair enough. And again, by defining the way we defined using all those axioms, we can guarantee that the norm are going to satisfy the properties that a norm should satisfy. Okay? So examples, state vectors and wave functions. So we are dealing with something that is much more general than just vectors in R3. We're really talking about entities that are more abstract and that we have seen a lot in quantum mechanics, but we are providing a unified view. And when quantum mechanics was constructed, people borrowed a lot from linear algebra and things that already existed. Moving on, a state vector is normalized when it has unit norm, meaning the norm is unitary. And if you want to know, if you are bored, and if you think you have seen these Axions, think again, because they were a roadmap for people dealing with pseudo-Hermitian and non-Hermitian quantum mechanics, and for non-Hermitian Hamiltonian systems. Because you have a system which is non-Hermitian, but which has real eigenvalues like your operator, right? What do? Your inner product, as we have just defined, doesn't work. Your norm doesn't work. You have to come up with something else, right? And that's what these people did. Okay, how do these axioms hold? Like the people who said, okay, we put a star here when you're dealing with a complex number so that the norm behaves in a way it should behave. What do these people do? For instance, if you're curious, Benda, Brody, and Jones, they defined CPT product. And before that, Ali Mostafazadeh defined a modified inner product in conjunction with pseudo-hermiticity, which I'm not going to discuss. So these people, they modify inner products for a living, okay? But they need a roadmap to assure that what they're doing is consistent. So that's why you need the axioms. And if you want to look at a nice review, there's this paper by Andrea Spring and myself, in which we focus more on time-dependent Hamiltonians because of the connection with strong field and attosecond science. But do have a look. And there's even a book which has just been published last year. And it's pretty much like everything you always wanted to know about non-Hermitian Hamiltonian systems are never there to ask. You find a lot of information there. This is quite useful. And the people who contributed, they are leading people in the field. So moving on, we need to talk about basis. We need to talk about dimension if we talk about spaces and vector spaces, because how do we generalize the concept of dimension to an abstract vector space? Okay, let's analyze what, if we say like intuitively, if we do some kind of hand-waving explanation, what is that we call dimension? Well, dimension is the number of entries you need to locate a point, right? For instance, if you have a plane, you need 2 coordinates and then you locate a point. If you have a space, you need 3 coordinates. You don't need more, but you cannot locate the point with less, if you see what I mean. So intuitively, that's what dimension is about. And we need to talk then about spanning set, because spanning set is when you have a weighted sum. Okay, need a pause. So just to continue, if we're talking about vectors and we really want to generalize the concept of vector spaces, we need to talk about dimension. And then we can ask the question, what is dimension? How do we define dimension? Well, let's look at the intuitive definition. If you need to locate a point in a plane, or if you need to locate a point in space, how many entries do you need in a vector to locate that point? In a plane, you need 2, right? 2 coordinates. In a space, you need 3. You don't need more, but if you have fewer entries, you're going to fail, right? So if you think about it, dimension is like the minimal number of entries in a vector that you need to locate a point. So moving on, what do we need to span this space? So if you have an arbitrary vector, let's call it V, you can construct this vector as a weighted sum of a set of vectors, let's call this omega j, and this alpha j that you see is like a weighting. So you have V equals sum over j, alpha j, omega j. And this is what we call spanning set, because you got a set of vectors and you're using that set of vectors to span space. But how do you know if you have more or if you have less? For instance, ijk is a spanning set for the R3 space, right? Because if you construct a vector x, y, z, you can see that you can construct it as a weighted sum of I, j, and k. But you could also use this, right? You could also pick up other spanning vectors. Why not? So this is a spanning set. You're spanning the whole space with those vectors. But what we really want is we want to use the smallest possible spanning set. So what we're going to do is look at the concept of linear dependence and linear independence. For instance, we call a set of non-zero vectors, v1, blah, blah, up to vn, linearly dependent, if there exists a set of non-zero scalars such that the sum that you can see here in the slide is 0. So in this case, they are linearly dependent because you can write one of these vectors as a function of the others, right? And a set of vectors is linearly independent if it's not linearly dependent. So if you have a spanning set with linearly dependent vectors, the set can always be reduced by removing vectors until it becomes linearly independent. This means that if it's linearly dependent, then you have something there you actually don't need. So you have some kind of superfluous vectors to define or to span your space, right? And just think about the concept of constraints, which you see a lot in classical mechanics or dynamical systems. What you're doing with that equation, which is used to define linear dependence, is you're constraining. So you don't have variables that are truly independent, right? So, for instance, I can use these 3 vectors to span R2, which is a 2-dimensional space, right? Why not? You can construct an arbitrary vector with them. As you can see below, you multiply them by some parameters, and by the definition that we have just seen, this is a spanning set. However, you can also show that this set is linearly dependent because you can write that relation. So this means that, in fact, 2 vectors would have been enough, right? So why do you have 3? And this is the concept. You reduce your spanning set until you get a linearly independent set. And then we need to talk about basis, which is a linearly independent spanning set. And the dimension is the number of elements on a basis set for a vector space. And this is what you say is called its dimension. For instance, the dimension D corresponds to the number of free parameters for a generic vector. So we come again to the point of constraints. You know, what is a constraint? Normally when you say, and you want to know the dimension of a space, you identify all the coordinates that you have, and then you look for constraints and you subtract the constraints from there. So it's pretty much in the same spirit. And for instance, dimension of Rn and Cn is n. The dimension of a state space of a spin n2 particle is n plus 1, just get spin half, right? You have that dimension is 2, spin down, spin up. And you can also have infinite dimensions. For instance, get a polynomial. The vector space of a polynomial is infinite dimensions. But what we see in these examples is that the concept of vector spaces has been kind of expanded beyond what we are usually familiar with. So let's move on and let's talk about orthogonality. This makes your life so easy because if you have an inner product space, you can say that 2 vectors are orthogonal only and only if their inner product is 0. For instance, in this case, these are the definitions we know for Dirac vectors and for wave functions. And an orthonormal basis requires that if you get 2 elements of the basis and you calculate the inner product, if you have a discrete set, you're going to get the Kronecker delta. And if you have a continuous set, you're going to get the Dirac delta function. And this is very useful for computations because you simplify a lot your life. You kill like enormous sums or integrals by using this kind of property. And we say here orthonormal because the norm is unitary, you see? And these bases that you're using, they are orthogonal. So the vectors of your basis satisfy these properties. You can use non-orthogonal vectors, by the way, but it's much more complicated and you have to be much more careful when you do your computations. So now, if you inspect the inner product in Dirac notation more closely, you see that it suggests a multiplication, right, between 2 objects, which is the bra and the cat. In fact, Dirac, when he was developing this, he thought about bracket. So that's why you have like bra and cat. And does it make sense? Can we talk about it? What is a bra? Because we spent a lot of time talking about cat. We said, okay, cat is a space state vector, a state space vector. So how about the bra? Well, it is a linear function and it's an element of a dual vector space. So I'm going to argue these 2 points here and I'm going to explain what I mean. So we need first to define what a functional is. A functional is a function which acts on a vector and gives you a scalar back, right? And that's what is happening here. If you look, you have this inner product, you come from the left with the bra, you act it on a cat, which is a state space vector, and you get a scalar, right? So, fine. And a linear functional is a functional such that if you act upon it with, if you act with it upon alpha 1 v1, alpha 2 v2, like a linear combination of vectors, you get alpha 1 f v1 and alpha 2 f v2. So it's a function that's linear, right? Because this is the concept of being linear. Remember the antilinear stuff we have just seen. So we can see that the bra represents a linear functional because if you act on, say, a cat, which is written as alpha 1 phi 1 plus alpha 2 phi 2 from the left with a bra, what you get is you pull the scalars out and you get inner products which are themselves scalars. So you acted upon vectors in state space with a function and you got scalars. So bra is a functional, tick. And then you satisfied the linearity condition. So it is a linear functional. Now, if we move on, we can also see that maybe bras can be thought of as vectors in their own right. Is this true? Because they look like, if you look at a cat in a mirror, you have something like a bra, correct? Can you think about them as vectors? So for that, we need to understand the concept of dual vector space, because for any vector space, the set of linear functionals acting on that space is belongs to a vector space V star, which is called the dual space of V. So this is, again, you're thinking about Alice in the mirror, you know, there was this book or whatever, but it is pretty much the concept that you can view them as vectors in their own right, but it's not going to be in the same space as the cats. It's going to be in the dual space of the cats. And examples, for instance, rows and column vectors, bras versus cats, right? So note also that in n-dimensional quantum mechanics, you can write a cat in terms of an element complex column vector. For instance, here, this is what pretty much we have done for a vector with 2 entries. And the corresponding dual vector would be the conjugate transpose vector. Because conjugate, why? Because you need to ensure the reality of your inner product. And transpose, because you need to ensure that when you apply the bra to the cat, that you're going to get a scalar, right? So moving on, we are done for today, and a lot of these things, they're very useful in the Hilbert space. So I hope to see you again. I hope you enjoyed this lecture, and the next part of formal quantum mechanics will deal with Hilbert space, which is what we are mostly interested in. So see you soon. Stay safe. Have a nice evening.